Amanda, no, sorry, Aria.
Can you do worksheet 3,
Worksheet 3, number 5. So it says you're sitting on top of your friend's 10-foot tall house. You notice a dog chasing a squirrel. You measure the angle of depression 40 degrees to the dog and 50 degrees to the squirrel. And then we want to know how far apart those two animals are, right? So remember, the angle of depression is always measured from the line of sight. So far, so good. So this is 40. And this is 50. And I want to find that x. What I notice is that like HD minus HS should equal x, right? Okay. So I can say here that tangent of 40 is equal to opposite over adjacent. Similarly, I can say tan 50 should equal opposite over adjacent. I can solve for HD and HS by multiplying both sides by HD and then dividing by tan 40. And then doing the same thing but dividing by tan 50. And that's all I need. Let's see. Change degree mode. And (20 over tan 40 divided by 20 over, or minus 20 over tan 50, I get about 705. So that dog's hot on that squirrel's tail. What's up?
What's the green and black?
Well, I'm just saying that like this distance minus this distance is going to give us this distance. So just like a geometry thing.
Okay, so H. Oh, okay.
So I'm just naming them like segments.
Okay. And then why'd you use
Because relative to the 50 and 40 degrees, I know opposite and I'm interested in adjacent. And tangent is opposite over adjacent. Aria, are you good with that? Paul. Sure. Okay. So we'll start by taking the inside part and using that to draw a right triangle. So remember that cotangent is adjacent over opposite. And secant is hypotenuse over adjacent. We know the adjacent side, but we don't know the hypotenuse yet, so let's find that. So using the Pythagorean theorem, I have that. So 1 plus x squared minus 2x plus 1 is equal to c squared. So square root x squared minus 2x plus 2 has equals c. So x squared minus 2x plus 2 over x minus 1. And I'm all done. Is that okay? Did you distribute the exponents instead of foiling?
No.
Oh, good.
I said negative 1 times
Oh,
negative 1 is not true.
no, not ever.
What did I do?
Arya.
In these questions, are like outside and side the same thing? Like, does it not do anything?
No, they definitely mean two different things. Arc sine describes how you're going to build your triangle. And then you use sine on a triangle. Like arc sine is going to describe what the triangle looks like. And then if you can't do sine until you have a triangle. Is that?
So what is it? Arc will all the time with all. What do you mean by it?
Well, cotangent is adjacent over opposite. So it tells me where to put the sides on my right triangle that I'm building. That the adjacent side is x minus 1 and the opposite side has to be 1. Maddie?
Do you have an A on this question?
Sure. Blake, did you have a follow-up to this question or something different?
No, I don't.
Okay. You're next then. 8. Okay. Just FYI here, Maddie, I'm going to think of 1/2 x as just x over 2. Because that just like makes life a little bit nicer. So I'm going to build my right triangle. Sine is opposite over hypotenuse. And tangent is opposite over adjacent. So I need to figure out what this adjacent side is. So using the Pythagorean theorem, I have x squared plus b squared is equal to 2 squared. So b is just going to be the square root of 4 minus x squared, right? Okay. So the opposite is x. The adjacent is root 4 minus x squared. And I think I rationalized the denominator when I did this. So I'll have x root 4 minus x squared over 4 minus x squared. Is that okay?
Yes. So then
And this was slightly simpler than if you had done 1/2 x over 1. Because then you had fractions inside of fractions. You'd have to mess around simplifying. By doing it this way, I got to avoid having to do that. Blake, you're next.
I would like number 5 on worksheet 7.
Oh yeah. This one is just poorly worded. I think is the biggest issue with this one. All right, so we're planning on sailing to this island. There's this much wind and this much current. and we want to end up going this bearing with this speed. So basically we start out with our initial settings. We interact with some wind and some current, and we have to end up at some final settings, right? The initial settings are what we don't know. The wind is, let's maybe call that a BW for bearing. It's 51 degrees. And we're going 9 knots. And then we have the bearing for the current is 281. And that speed is 13 knots. And I need to end up going at a bearing of 114 degrees with a speed of 22 knots.
Wait, so, but why wouldn't the bearing be initial?
What's up?
So why wouldn't, it says that they would have to go at a bearing of 114 to get to the island.
Right. You set that bearing and then you run into
yeah,
wind
and
and
that's not
current,
counting.
you're going to push you all over the place, right?
No, okay,
So our conclusion is here, our initial is going to be related to the final minus the wind and the current. And that's the setup for us. You buy that as like an explanation of what's going on?
yes.
Okie dokie. Do we need to grind this thing out?
No, I mean, if you want to.
I mean, if it's your question, homie, if you want to, I will.
No, I didn't really know what was going on in this one.
It was poorly worded on my part.
I need to be more critically thinking.
Nah. I did a poor job of wording it. I should have put all the final information all in one place, and it would have been a little bit more clear what the heck was going on. And then I think some of the wording made it clear as to like how when is the vote going 22? Is it at the initial or is it at the final?
Okay, thank you. That makes sense.
Yeah, my apologies. Jacob. Sure. All right, so our boy Gilligan, he's going on a trip here. He makes one turn, he makes another turn, and we're asking how far away and where is he at. All right, so I'm gonna just break this into like 2 legs for my journey. So on the first leg, we do a bearing of 108, which is like there. But I need to translate that into a standard position angle. So that's going to be 360 minus 18, so 342. And the speed on that, we're going 35 knots for 2 hours. Oh, I'm sorry, we're lining distance. 35 knots for 2 hours is 70 nautical miles. And then our second turn, we go 286 is our bearing. So over here. So again, our theta then is going to be 180 minus 16, so 164. And our distance is going to be 45 times 2, so 90 nautical miles. So our x component, 70 times cosine 342. Our y component, 70 times sine 342. And our x component, 90 times cosine 164. Our y component, 90 times sine 164. So our final position is x1 plus x2, y1 plus y2. Notice we're adding because we go one turn and then another to get to our final, right? Hopefully that part is pretty obvious. Where's my mouse? There it is. Make sure I'm in degree mode. I am. So 70 cosine 342 plus 90 cosine 164. So that's negative 19.94. And then we got to do the same thing except with sines in there. And that's 318. So the distance is easy to calculate. That's just the Pythagorean theorem. Jacob, doing so far so good? Okay, holler at me if I'm going too fast or buzzing through something you're not quite sure about. Same goes for anybody else. So that gives us a distance of 20.19. And then to the bearing, I'm going to graph that point of negative 19, 3.1 whatever. So that's our bearing. So 0, 90, 180, 270, where that's my alpha. So my final bearing is going to be 270 minus alpha, where the alpha is always tan inverse absolute value y final divided by x final. Oops. Try that again. Forgot the absolute value, and I got some yucky negatives rolling in this problem. We doing okay? All right. There we go. So I get about 260.95. That feel okay there, Jakeruski?
The key says
279. Oh, yeah, of course it would. Why would it say 279? Mr. Kulik, you're a moron. Look at the picture you drew. Did you graph negative 19, positive 3? No, you graphed negative 19, negative 3. So that should be plus alpha. Mr. Kulik, you are so dumb sometimes. I'm trying not to be, but like, you know, like graphing points is hard sometimes, guys. And there's my 279.05. That's better. Cool with that, Jake Arai?
Yeah.
Cool. Who wants to go next? Sorry about making the mistakes on that. I'll try not to let it happen again. It's not bad for doing these all off the top of my dome, though. Peyton.
Can you do 16 on the problem test?
Yeah, of course. So this is a pure calculator question. All right. So it's asking me to find the value of this cosecant inverse of negative 1.5 over this interval. So first thing I want to do is I notice this interval is in radians, so I should turn my calculator mode to radians. And then what I'm going to do is I'm going to graph cosecant, regular, and negative 1.5. Cool. And I'm going to change my window to go from pi over 2 to to 3 pi over 2. Just like it's given there. And then I'm going to hit graph and look for the intersection. So there's my intersection. So second trace, intersect command, enter, enter, enter. So my answer should be about 3.87. Is that cool?
Yeah.
So the only trick there is just using the regular version in the graph, and you're graphing like, rather than thinking about this as theta equals cosecant of negative 1.5, we're just going to do cosecant theta equals negative 1.5. And that's basically, we're going to graph both sides of that equation, find the intersection. Because that has lots of answers, infinitely many answers, but only one of them lies on that little interval. If you could graph that from negative infinity to positive infinity, you'd have infinitely many intersections, but we only care about one of them. So you just find that one by narrowing it down. Is that cool?
Yeah.
Yeah, I'm happy to do it. Who else has some? Sure. Okay. Well, if you guys change your mind, we can always talk about some more later. You guys all right? Let's start chapter 5 then. So section 5.1, we're going to talk about some fundamental trigonometric identities. So when we talk about an identity, we're talking about something that's true for all values for the given variables. So like, the Pythagorean theorem is technically an identity, right? Or like 2x plus 6 equals 2 times the quantity x plus 3 is an identity, right? For any values of x, that's going to be true. So we're going to talk about a whole bunch of these different classes of identities today. We're going to start with ones that we already know. In fact, I would say all the identities today we're really are things that we might have or already have observed, whether we knew it or not. Uh-oh, what just happened here? Okay. So the first class of identities we're calling the reciprocal identities. So you probably remember way back in chapter 2 that there was for sine, cosine, and tangent, there was a reciprocal reciprocal function for each of those, cosecant, secant, and cotangent, respectively. So we're just going to codify that into an identity for each of these. So we know that sine is equal to cosecant, or 1 over cosecant, excuse me. Cosine is equal to 1 over secant. Tangent is equal to 1 over cotangent. And then, obviously, cosecant is equal to 1 over sine. Secant is equal to 1 over cosine. And cotangent is equal to 1 over tangent. These are ones that we already basically knew, right? We've talked about how these pairs of functions are really reciprocals to each other a bunch of times. So far, so good? Okay. So there's 6 of those. We also have the quotient identities. So remember back when we talked about the unit circle, that tangent was equal to y over x. And on the unit circle, the y coordinate is sine, and the x coordinate is cosine. So we can really say that tangent is sine over cosine. And since cotangent is the reciprocal of tangent, I know that cotangent is cosine over sine. Everybody okay there? Okay. So if we go back to our unit circle here, if I pick some point on that unit circle xy, and I build a right triangle like this, I know that like x squared plus y squared is equal to r squared, right? Anytime I have a circle and I pick a point on the circle, that's got to be true. Okay, well, on the unit circle, x is cosine theta, y is sine theta, and r is 1. The radius is 1. So we can say that cosine squared theta plus sine squared theta is equal to 1. And here, just a little piece of notation. Notice that if we put parentheses and the squared on the outside, that's going to mean the same thing to us as putting the squared next to the cosine and in between the theta. Because mostly we're lazy and we don't want to have to write those 2 extra sets of parentheses every time. And if we didn't put the parentheses there, it'd be a little confusing. Are we talking about squaring the theta and then doing the cosine? Or doing the cosine and then squaring the result? Yeah, this is the notation we're going to use to try to be unambiguous about that. Okay? So this means you do the cosine and then square the result. Everybody okay with the notation there? Okay. And we can make 3 different versions of this equation. So for example, if I wanted to divide both sides by say, cosine squared. Cosine squared divided by cosine squared is just 1, right? That should be easy to see. We said sine over cosine is equal to tangent right above. So sine squared over cosine squared would be sine over cosine times sine over cosine. So you have tangent times tangent, or tangent squared. Then we have 1 over cosine squared. Well, I know 1 over cosine is secant. So 1 over cosine squared is just going to be secant squared. Everybody's okay there? And say instead of doing cosines, what if we had divided by sine squareds? Well, cosine squared over sine squared is going to be cotangent squared. Again, we noticed just a moment ago that cosine divided by sine is cotangent. Sine divided by sine is 1, or sine squared divided by sine squared is 1. And 1 over sine squared is going to be cosecant squared. You guys cool with that? These three identities we're going to call the Pythagorean identities. We all cool there? Okay. The next class of functions is called, or identities, is called the cofunction identities. So some of us might have noticed that there is a relationship between, say, sine and cosine. If you're talking about angle pairs that are complementary. So you might have noticed that, say, the sine of 30 degrees was equal to 1/2. And cosine of its complement, cosine of 60 degrees, is also equal to 1/2. Did you guys notice that at any point on the unit circle? That's actually true for all complementary pairs. So we'd say that sine of theta is going to equal to cosine of its complement. Or we could say cosine of theta is equal to sine of its complement. Now, if this is true for sine and cosine, it's got to be true for their reciprocals. So we could say cosecant theta is going to equal to secant of its complement, or secant theta is equal to cosecant of its complement. Remember that pi over 2 is 90 degrees in radians, right? So pi over 2 minus theta is just the complement of theta. Right, everybody's okay with that? Okay. And then similarly, you might have guessed that tangent and cotangent are going to have the same complementary identity. as an unimportant aside, you notice that we have like sine and cosine, secant and cosecant, tangent and cotangent. The prefix co is actually short for complementary, because these are complementary functions, in that they are equal if you're operating on the complement. And our last set of identities are called the odd-even identities. You remember back when we graphed the sine function, we noted that it was an odd function. Since sine is odd, we know that f of negative x is equal to negative f of x. So we can say sine of negative theta equals negative sine theta. And since sine was an odd function, cosecant necessarily, its reciprocal also has to be an odd function. As soon as my pen wants to write, I'm going to write that down. Oh my gosh, come on now, pen. Just try taking the battery out and putting it back in, because I don't know how to fix anything. But I feel like that's always a good starting point, right? Something stops working, just turn the power off and try it again. Oh, look at that, it did work. Okay. We remember that cosine is an even function. So I know that f of negative x is equal to f of x, or in our case, cosine of negative theta is just equal to cosine theta. And if that's true, it has to also be true for its reciprocal. So secant negative theta is equal to secant theta. And lastly, remember when we talked about tangent, that was also an odd function. So we can say the same thing about tangent that we did for sine. And if it's true for tangent, it's got to be true for cotangent. That's a goofy looking theta there, Mr. Kulik. Luke.
So what made a function odd?
So we observed this when we were graphing, right? So for example, when we graphed sine, like one period looks like this. So when the opposite quadrants are like reflections of each other like that, that was indicative of an odd function. Cosine, you know, if I do one period of cosine, it kind of looks like that, which is even. And then tangent, similar to cosine, was, you know, like that. Also odd. But we noted that just graphically. You cool?
Yep.
Okay. That's a terrible job of graphing tangent. Needs to go through the origin. Needs to go through the origin. Needs to go through the origin. Close enough. I don't care anymore. I can't draw. Okay. Feel good about the identities? That's the list. Most of these are things we are already kind of aware of. I'd like to point out to you guys that I've already condensed these onto a single sheet of paper for you and typed them all out for you nicely. That's all in the content library, so make good use of that. And actually, let's do this before we get any further. I'm going to take this and put these notes over here in chapter 5. That makes a heck of a lot more sense, huh? Hooray for OneNote, makes it so easy to do that kind of thing. All right, let's look at some examples here of ways that we can kind of apply these properties. So let's say we're asked you to find sine theta if tangent theta is equal to 3 and cosine theta is negative. All right, so what I'm going to do is I'm going to search for my identities and see if I have anything that relates sine and tangent together with only those two functions. If I take a look through here, I got nothing, right? You guys agree with that? So what I'm going to do instead then, well, let's look at, see if there's something that relates tangent and cosine together. I don't have anything that relates those two directly, but I got something that's pretty close. If I look at my third Pythagorean identity, I know that 1 plus tangent squared theta has to equal secant squared theta. And I know that secant and cosine are reciprocals of each other, right? Okay. So since tangent is 3, or tangent theta is 3, I get that secant squared theta is 10. Oops. Or that secant theta is plus or minus the square root of 10. Everybody's okay with that? And I know that secant and cosine are reciprocals. You guys good there? Since cosine is negative, I know that this then has to be a minus. And then I know tan theta is equal to sine over cosine. If I want sine, though, I multiply both sides by cosine. So I have negative 1 over square root 10 times 3 equal to sine theta, or when I rationalize my denominator, negative 3 root 10 over 10. Was this the only way you could have done this? No, right? There's probably lots of different combinations of identities you could have used to sort this out. Luke?
I'm confused why you use tangent at the end there.
Oh, Well, if I want one thing that uses all three of the things that I know about, sine, cosine, and tangent, that's an identity that uses all three of those things. Right? Because at this point I know cosine, I know tangent, I'm looking for sine.
Okay.
So I looked for something that had all three of those things in there. You good with that?
Yeah.
Okay. And some of these are just like, you just got to kind of play around with them a little bit. But basically you're just plugging something in to one of these identities to solve for another value. You might have to ideally get the, if you're told something is negative or positive, you're probably going to need to use a Pythagorean where you have to do a square root so you know whether you take the positive or negative one. And then put it back together. There's not really a like, you must always do this, this, and this. It's just kind of like, playing around with it a little bit. Let's do a different kind of example. So let's say we're asked to simplify this expression, sine cubed x plus sine x times cosine squared x. So the two things that you'd be looking to do on a problem like this is you can either look to use some basic algebra stuff, or you can look to use an identity. And you may have to do both or combinations of those. That's all okay. Luke, did you see something you wanted to do here?
Yeah, you take out sine.
Excellent. So yeah, if you look, you notice that there's kind of two terms here because you have two things that are added together, both of which contain a sine x in them. So I would start by factoring out that sine x. When I factor that out, I have sine squared plus cosine squared left. Everybody cool on how I did that factoring there? Okay, now what? Yeah. So we have an identity for sine squared x plus cosine squared x. That's one of the Pythagorean identities. So that's just one. And 1 times sine x is just sine x. Once you've got it down to a single trig function, you know you can't go any further than that, right? So we're good. Done. Simplified. Questions about that one? Let's do another. Let's call that one A. Let's make this example B then. Okay. So let's say we have secant x minus 1 times secant x plus 1, all divided by sine squared. Anybody with an inkling what you might want to do first? Luke?
Did you get the secants to be
Okay, we can do that. Now I'm going to state for the record, this is okay to do and it's not going to really screw anything up. This is not what I would do, mostly because I find it more difficult to work with fractions inside of fractions. But it's okay. It'll still work. It might get a little hairy. Okay, so we can do that, right? Now what do you want to do?
And then sine squared would be 1 minus cosine squared.
Okay. I'm not sure where we're going with this, but let's play it out and see where we're headed, because sometimes you guys see clever ways of doing things that I don't find or I don't see immediately. Okay.
I was just thinking get it all to cosine and do something with the fraction.
Okay. So this is all not, Luke hasn't made a mistake to this point because he's used identities, made legal things. If we're going down this route, what you would need to do next is make a common denominator in here. But this is getting kind of messy, and I'm going to suggest stopping here and suggesting a different track. So instead, what I would do is I'd start by foiling the numerator. I see I have something plus 1 and something times something minus 1. That to me screams a difference of 2 squares. Anybody else hear that screaming now that I pointed it out to you?
I thought that was a minus. Is that a plus? Is that a plus?
Yeah, that's supposed to be a plus 1. So yeah, that's what I would do here. So you're going to end up with secant squared x minus 1 over sine squared x. Is everybody okay with that? I've skipped the foiling all the way out and just used my difference of 2 squares formula to kind of do the multiplication there. Although if you want to foil it all out and cancel things, like, that's cool. No biggie. I'm into that whole brevity thing. Do you guys see anything good to use here? Might I suggest I'm going to swap 1 plus tangent in for secant squared. Because then the plus 1 and minus 1 can just cancel out of there. You guys good with that? And now this is much better because I've gotten rid of all the addition and subtraction, which is a massive improvement, right? That makes simplifying much, much easier if everything is just multiplication, because then we can just do some normal stuff here. Well, or whatever. I'm going to think about this now as tangent squared theta times 1 over sine squared theta, so that it'll be easy to line things up to cancel out. And now I'm going to rewrite tangent as, or tangent squared, I should say, as sine squared over cosine squared. And since there's no addition or subtraction anywhere, I can do that. Which is just secant squared theta. And again, now that I'm down to a single trig function, that's as good as you're ever going to be able to do. Now, these are going to be tricky in the beginning. Like, there's no sugarcoating that. Like, some of us are going to catch on right away. Some of us are going to struggle bus on this for a little bit. It's okay. Let's do some more examples. Don't be frustrated. It sometimes just takes a little bit of time. Anybody got some ideas on this one?
Find a common denominator.
Yeah. There's no obvious identity involved here, right? Anything that you tried to do is just going to make fractions inside of fractions, which is typically a bad idea. So let's just make a common denominator. What would that common denominator be in this case?
It would be just sine times 1 minus sine times cosine.
Very good. So I'll multiply the first fraction by cosine and the second fraction by 1 minus sine x. Everybody okay here? Looking good? And I'm just going to pause here for a moment and mention that notice that in all these steps, I'm always keeping my variable. I notice that a lot of times on these that students will stop carrying their variable and they'll just, instead of writing sine x, they just write sine. I'm going to mark down if I see that on test or quiz, just as a heads up. It'd be like saying, oh, square root symbol. And just writing the square root symbol with nothing underneath it on a paper, like you wouldn't do that, right? So I'm just going to let you know, as we're talking about these things, that that's something that's a pet peeve of mine, and I will be picky about it. Before we start getting and doing a bunch of these and you get used in the habit of forgetting about the variables. Okay, anyways. So what do we have here? We have cosine times cosine is cosine squared. And then sine x is going to distribute through. But I'm going to leave the denominator kind of in that factored form, because if I'm going to do any reducing, I have to factor the denominator anyway. So like, why would I bother multiplying it out when I'm just going to have to factor back later, right? Okay, everybody's okay with what I got here? Do you notice anything good that you can do? Something should be screaming at you. Yeah, we have cosine squared plus sine squared, right? Everybody get that? What's that? 1. Whoa, look at that!
So insane. Absolutely.
Now, be careful there, because when you cross those out, you still have a 1 left in your numerator, right? And we'll just call that secant. Do they always end up being secant? We've had like 3 in a row that have some version of secant. The answer to that's no, of course not. That's a silly question. I'm glad you all laughed when I posed that, or many of you did, and realized that that was a joke, because it definitely was. Just a happy little accident. Let's do another one. Okay, we have sine x times cosecant of negative x. what you want to do first. Yeah, we got the variable parts have to be the same in order for us to multiply or add anything together. So let's use the odd-even identity to rewrite cosecant as negative of cosecant negative x as negative cosecant x. Be cool there. So if I just multiply those together, I can write it this way then. We'll just, the more traditional, plug the negative all the way to the front, right? But I figure if we're looking at notes, it's a lot easier to see what I did if I write that first. Yes, sir.
So then can you just make that negative 1 over secant for the sign?
Okay, you mean 1 over cosecant?
Yeah.
Sure. You got it, dude. The trick there is making sure you deal with that negative sign straight away. You got to get that negative out from inside of the trig function before you can proceed. And I got one more example for you, and then we'll call this a day. How do you guys feel about that?
Yeah.
Party time. All right. Say we have cosine of, oops, are we letter D or something, I think. Something, I don't know, whatever, alphabet. So we have cosine of pi over 2 minus y times the quantity cotangent y plus tangent y. What do you want to do here? There's lots of things that got to get taken care of. What would be the first thing you might want to take care of, Dominic?
That cosine is sine.
Yeah, let's get rid of that cosine of pi over 2 minus y. We can use our cotangent or cofunction identity just to do that. That way, all the variables are just y's. That looks pretty righteous. Now what? Anybody with an idea here? If we're stuck, not a bad thing to do is just to rewrite everything in terms of sine and cosine. So if I do that, I'm going to rewrite tangent or cotangent as cosine over sine, and rewrite tangent as sine over cosine. Oops-a-daisy. Those are supposed to be y's. That's not a bad thing to do if you're just, I'm not sure what to do anymore. Try writing everything in terms of sine and cosine and then just doing some algebra. What do you want to do here? Well, it's not 1 because it's not, you don't have a common denominator. It's not being multiplied, right? It's being added. That's what you're saying?
Sorry.
Yeah, that's okay. These are things that, like, shout out those initial thoughts, and it's okay to be wrong, right? We get to talk about why it's not appropriate to do that, and that helps everybody because I'm sure you're not the only one that's thinking like, hey, that just all cancels out, right? What if it was multiplication? But we're adding. Yeah, let's make a common denominator. What would the common denominator be? Yeah, it would just be sine times cosine, right? So this first fraction will multiply the top and bottom by cosine. And the second fraction will multiply the top and bottom by sine. So don't forget about that sign out front. And I'm just going to write a bracket here because it's starting to get kind of like a lot of parentheses here. That look okay? Now what do you see, Dom?
You can change the top. One.
Exactly. That is our Pythagorean. Now what? Yeah, it's really not even distributing though because there's no multiplication, right? So you can just do that. What do you see? Cancel the signs. What do we get? Which is the same as? Secant. Oh, Mr. Kulik. What a sense of humor. All right. We'll stop.